Hello and welcome to the Minnesota Stormwater Seminar Series. My name is Andy Erickson and it is my honor and privilege to welcome you to the seminar today. I'm very excited for our keynote presentation. We will be talking about defining the footprint of sediment in green stormwater infrastructure. This seminar series is funded through the University of Minnesota Water Resources Center, the Clean Water Legacy Amendment, the Clean Water Council of Minnesota, and is in partnership with the Minnesota Pollution Control Agency and hosted here at St. Anthony Falls Lab. We're so happy to have you with us today. We will start with our keynote presentation, which we will start momentarily, and then we will have a panel discussion with local experts, including our invited keynote speaker. Our keynote presenter today is Dr. Virginia Smith, who is an associate professor of civil and environmental engineering and a principal investigator in the Villanova Center for Resilient Water Systems at Villanova University. You might not know, but Virginia actually has lived in several countries during her career in life and speaks some languages better than others, but way more languages than I speak. So if you have a chance to meet Virginia and talk a little more with her, she's very fun to talk to and learn about. Her presentation today, though, will deliver the keynote, Defining the Footprint of Sediment in Green Stormwater Infrastructure. And with that, it is my pleasure to welcome Virginia up to the stage. Please help me welcome Virginia.
Thank you so much. I'm so happy to be here today. And it's been so nice to learn about the many things that are happening here in Minnesota, the research here at SAFL, and everything that's happening around stormwater here, which is really exciting. We've been thinking about this a lot at Villanova too. And so it's cool to see where things line up and also some of the new ideas that are coming out of here and the new challenges that we're facing maybe together, maybe things that are on the horizon for both of us. So I think I can do this. Let's see. I can click on it. Oh, okay, that works. There we go. So I'm here visiting from Villanova University. It's just outside of Philadelphia, and I'm part of the Villanova Center for Resilient Water Systems, which is a whole lot of investigators, which we have up here. And a lot of the work that I'm going to be talking about today features things that I've worked on with many of these great people that are on the screen: Bridget Wadzik, Rob Traver, Kristen Sampelord, Kelly Good, John Comlos, and we're all civil engineers up here on the top, but we also have this group of people from other disciplines that we work a lot with in robotics and sensors, artificial intelligence, and in general, we're interested in urban systems and watershed processes, and also how we interact with communities and how to engage communities in infrastructure moving forward. And so we're looking at a whole lot of different things, but today I'm going to talk about sediment and how sediment interacts with GSI. So I borrowed this image from Minnesota's Stormwater Manual here. And this is probably something you're all very familiar with. You have water coming in, you're using nature-based processes, infiltration, evapotranspiration, to manage this water and attenuate the flood pulse that's coming through here and also clean the water up, take some of the stuff we don't want in there. And in Philadelphia, we have what's called the Green Cities Clean Waters program, and they have put in a lot of GSI across the city in relatively few years. See the same thing in New York, the same thing in Portland, the same thing in China, in Zurich, Switzerland, where I do some work with the Swiss National Lab, IAVAG, and they're doing a lot on this too now, thinking about green infrastructure, less from the stormwater perspective, but more from the perspective of urban heat mitigation and biodiversity enhancement. And then, of course, here in Minneapolis, there's so much going on. We have so many of these programs, right, being installed everywhere. But these are open and often very messy systems because our urban environments are complicated, right? It's complicated. And you've got all of this coming in, as well as your precipitation. You also have whatever's happening on the land surface flowing into these systems, hopefully being caught and captured and mitigated as any water makes its way out into the environment. But you have all of these co-benefits that are coming off of these systems too. So what does this mean for how these systems function over time? If these are open systems, then they're changing, they're dynamic systems, they're alive and living. And what we know, what we can see in literature, and this is from the Del Grosso study in Northern Virginia, looking at what caused these systems to underperform, was that sediments and blockages, debris, erosion and bare spot, a lot of this is related to sediment transport. Aspects that are causing these to underperform, and this isn't always the case. These are very broad questions, right? But a lot of times sediments coming in to the answer of why these are underperforming. So today, I wanted to talk about the fate of this. What's the journey of sediment? Where is it coming from? In the watershed processes, what are the factors that are contributing to the types of sediment that you're going to get in your system? How does the curb cut inlet specific to infrastructure, how does that sediment capture efficiency shift under different drainage and flow conditions? And then finally, now the sediment's been generated, it's made its way into the inlet, and now that it's into the GSI component itself, how does that sediment advection and dispersion work as sediments moving through the system, and how does that impact the function of these systems itself? So I'm going to break the presentation down with these three different parts, starting with watersheds and thinking about where sediment's coming from. What's an urban sediment? Nobody really knows. So we started looking at all of the sediment data we could get our hands on. And we took data from the US and Switzerland, Australia, Canada, and see my map's gotten a little skewed here, New Zealand and Australia. And then we also started collecting data in Philadelphia too. And we paired this data together and started looking at the land use characteristics, the climate conditions, drainage areas that it was coming off of, what type of land cover did this sediment represent. And then we looked at the total concentrations, the mean grain size, the sampling, and the analytical method of these. And what we found was pretty interesting. First, we found that there's not a ton of sediment data out there. It's hard to get. But also we found that looking at the sample collection method varies the type of results that you're going to get a lot. So here you can see we have data collected using an auto sampler, data collected using grab samples, and then other methods. Auto sampler is only going to give you a certain range of particle size distribution. So this is based on our D50. So you can see that there's no real statistical significance between the auto sampler values that I have here. However, when you start comparing this to the grab sample and also some of the other methods that are used, you get very different values for your D50. So if I'm comparing sediment data across the globe, it's not fair for me to compare things that are statistically different from each other, right? It's no longer apples to apples. Now I've got auto samplers to grab samples. And so we took this into account when we started looking at our data, but we said, all right, well, the way I'm collecting this data matters a lot, but what about the analytical method? So we looked at how the D50 was sampled through different analytical methods. So here we're looking at the sampler method, but we're also looking at the particle size analyzer versus a wet sieve and particle size analyzer together, and then other methods. And there's no statistical difference between the particle size analyzer and the wet sieve paired with that, but there is when we start using other methods. So taking that into account and trying to narrow this down where we didn't have statistical differences between our samples, now we can finally start looking at the samples themselves and saying, all right, what does it mean if my drainage area or my land cover changes? So we looked at the D50 versus the TSS, the total suspended solids. And we found something really interesting. So here we've got T50 based on different types of drainage areas. And we used this based on roadways because this was available in the data a lot, but we could compare these too. And what you see is you've got parking lots that are a bit lower with a D50. And then this is increasing. And really there's no statistical significant difference between these values. But highways has a much greater range of possibilities that are coming out of this. And we tried to look at the climatic zones of this, and things quickly fell apart. We tried to look at the vehicle traffic, which has to be impacting this. If you have a highway that gets a lot of use versus a highway that doesn't get a ton of use, your wear and tear on that road is going to be different. I imagine the freeze-thaw cycles between Philadelphia and Minneapolis are going to be pretty different, right? Unfortunately, because of the limited number of samples that we had, you couldn't really tease out those values in any kind of significant way. When we looked at the TSS concentrations, things were even a little bit messier here, But what we could see is that generally, highways and roads that were getting a lot of use at faster velocities had greater values of our D50 and less TSS compared to some of our smaller roads. So parking lots were having smaller particles come off of them compared to secondary streets, arterial streets, and highways like that. And so we could start thinking about these from different types of categories, that maybe what's coming off of your drained surfaces differs depending on what that surface is, right? And this is going to matter because we want to manage the sediments that are coming into our GSI, right? To make sure that these keep functioning over time. So then we said, all right, well, how does this compare to our best possible modeling of sediments? And the only way we really have to do this at the city scale, there's not a lot of options for us, but to use soil loss measurements and soil loss equation. So we decided to pair this in Philadelphia with the revised universal soil loss equation here, and we used a small drainage area, and then we also collected data at this drainage area. So we calculated the Russell equation for the entire city, but then collected it for the small area shown here in red too. Now the blue area shown here, where we used a dirt bag and we paired this with TSS data. So the dirt bag, not just because I hate this device, that's the technical name for it, the registered trademark, but this dirt bag collected all of the sediment, and then we paired that with TSS data to make a particle size distribution of what we think the sediments look like coming off of an interstate in the Philadelphia area. And then we could also compare estimates for the load. And when we did that, we compared that test data to what was estimated by the Russell equation. Whoa, that's quite a difference, right? So here the Russell equation estimates a really low mean generation in tons per hectare per year versus the data that we're actually collecting is much, much higher for what's coming off of those impervious areas. Because we know that those impervious areas are dynamic and they break down, and you have things that come off of cars and stuff that we've all seen in our GSI, right? And so what does this tell us? That we very much need a new way to model this, because not only do we not know what urban sediment is, but we really don't have great estimates for what's coming into our systems. But we know that these can be detrimental to our systems over time and take a lot to maintain. So we started thinking about, well, how can we predict maybe where some of these sediments are coming from? And so we started looking at construction that was happening in Philadelphia. And then we looked at the soil loss that we estimated that we know is an under prediction, but we paired this together then to estimate a guess at what we think the ultimate sediment generation might be, or the likelihood. So we put this on a scale of 0 to 1, 1 being the highest, 0 to being the lowest, to say this is our estimate for what we think an index for sediment generation would be on a scale of 1 to 0. How likely is this spot to generate sediment? And then we paired that with a litter index and also a leaf index to come up with an overall index of what we believe will be flowing into a potential GSI, an inlet at a certain point. And we paired that with drainage areas then to come up with a maintenance severity index. And this work is the work of Kate Homa. It was published in 2022 with Dr. Pelle Kramer, also from Villanova University. So once we came up with the severity index, then we could do a hot and cold spot analysis to say, how much maintenance do we think GSI across the city are going to require? And once we could think about the maintenance, well, that's not the only thing that goes into this, right? There's a lot of so many other things, and I'm sure many of the people in the room know this far more than I do, about the planning of where you select a site for a GSI. And so we thought about the inundation potential. How big are the GSIs? What's the built environment need? How dense is your urban landscape? How much green space do you have? What's your social need? And then finally, what are your maintenance needs? And so we put this all together to come up with some type of overall need and try to think about balancing the needs for these GSI in different locations, and also what's going to go into keeping these GSI going over time. And so when we put this together, we ended up making this theoretical matrix of the benefit And here I'm calling it BGI, Blue and Green Infrastructure, just another, we have so many names for these, right? So BGI benefits versus the BGI maintenance severity, and how much are you getting for the cost of maintenance over time, right? And could you then think about where your high maintenance risk is, maybe the need to invest in something that's maybe a lower potential for benefit, but a lower risk of maintenance, right? So trying to think about these in terms of a matrix that would balance out the benefits and the needs. So the takeaways from this, what I just wanted to highlight is that sediment can vary a lot across an urban landscape. Your cities change neighborhood to neighborhood. What's happening with your green space, with your tree canopy, is all playing in to the function of your GSI over time, right? And if we know what to expect in terms of our sediment inflows, our litter, what's going to be driving some of these larger maintenance questions, then we could design for it. We could pick GSI type based on what the benefits we need as a community, but also the maintenance needs that are required. If I have an area that has a ton of trees, then certain types of rain gardens might be a lot of work to have to rake out all of those leaves constantly, right? Depending on where I am. And that this is always a balance between the requirements and the needs of a GSI when you're implementing them and the benefits that you're getting out of this. So thinking of this more as an overall system and moving away from individual components too. And so thinking of these as systems, this brings me to the second part of this. Characterizing sediment capture. And here I've got a couple images of sediment capture. I've become one of those people that every time it rains, I have to stop and take pictures of the inlets, and I make my kids do it. And we're walking down the street and Mom, I'm just gonna take pictures of this again. But it's a really interesting thing to think about what's going into the inlets and what's not going into the inlets. And Bridget Wadzik and I started thinking about this a couple years ago, and working with Hussein Husseini and Richard Ampelma, and just recently Dr. Wisdom Akutu, who just got his doctorate last week, and he's the one who I'm going to be presenting some of his work in this section and in the previous section. But thinking about what's the capture of these areas, but also how much sediment's going in with these different systems. So when you put an apron onto an inlet, how is that affecting your capture rates? When do you expect that you might get clogging of these inlets because of different aprons and things of that nature? So we built this physical model in our lab, and we made a roadway surface and a curb cut inlet. And several years ago, starting in 2018, we started doing some experiments just looking at the water on this. And so we have a PVC board surface with a circular curb cut inlet, and we 3D printed all of this, but we have different types of inlets that we've printed so we can replace the curb cut there. And then we collect data on the curbside and also have a bypass collector and a water flow meter at the top. And then my favorite, the sediment feed. So just in the past year, we've started putting sediment into the system to think about how this collects sediment and the percentages of that. So this is just looking down at the top view of this, where we have water flowing across from the water supply down to these collection points at A and B here. And so what we found, here we have the capture efficiency, and this is, we can tilt the surface, so we've tilted it longitudinally in 1 and 2 degrees, and then cross-sectionally in 2 and 5 degrees. And so you can see the different slopes here, and that your capture efficiency initially is pretty high. Initially, it's up at 100% for the cross-sectional slopes. You're capturing pretty much everything. And then as you turn up that flow rate, your capture efficiency goes down and down and down, and you get a lot of bypass through these systems. And we've all probably seen that walking down the street, where you see when it's really raining, those intense summer storms, and water just shoots right by the inlet of that GSI. Come on. Sorry, got excited and hit the mic. All right, and this was nice, because this is our research from 2021, and this is, here we've got sediment laden water. So this is water and sediment on the first graph, and then the second, this is just our water capture efficiency, and we're like, it matches, perfect, that's easy, we scienced, that's great. But then when we started thinking about this in terms of sediment concentration, oh, it looks a little different. Things are more complicated, right? So as that flow rate goes up and up and up, initially, yeah, we're getting a ton of capture. We're getting 100% of the capture compared to the bypass, but the actual concentration is really low because we have a lot of sediment left behind on the road. And I saw that just the other day when I was driving in yesterday on the interstate. You can see little islands of sediment left behind because there's just not that shear stress to get it up and moving. You need a pretty good flow. And then once you get that higher flow around 8 GPM here, then you're starting to get a lot of bypass associated with this too. So we started thinking about that sediment concentration and what's actually happening. And at these steeper slopes, you're able to mobilize a lot of the sediment, but you also have so much momentum that you're getting so much bypass around these systems too. Whereas with the gentler slopes, you build up these bars on the top end. You're depositing a lot of sediment that's not able, you have a lot of sediment that's not able to move. But around 8 GPM, this is where you're maximizing your capture rates for sediments. And then you're getting a lot less bypass that's happening. Well, we started scratching our heads about it because I just can't leave anything alone. And so then we started turning this into what if instead of thinking about this as concentration, because 8 GPM, that's a lot more water. And we're thinking about, like, a lot of what we're talking about is just water. What if we just look at the mass of the sediments? And so when we just looked at the mass of the sediments, you can see that your capture efficiency for your high cross-sectional slopes, if you were to put an apron on your inlet and you have like a 5% slope, your capture efficiency is incredibly high. But you start to lose some for these lower slopes at the higher GPMs. That's where you have that momentum and the sediments just going right by. And so what we saw was more sediment captured at the steeper cross-sectional slopes, had a lot of bypass at the more relaxed slopes, and then lots of sediment retained as expected for those low discharges, just not a lot moving through the system. So when we compare, and the solid line shows the inlet capture and the dashed line shows the inlet bypass, when we compared these two together, there was still a little bit that just wasn't quite matching up between this concentration. And so we said, well, what if we thought about it then in terms of the type of sediment? Because fines are moving in a different way than sands are. So we started thinking about it that way. And here I just have a quick image of the bar that's been deposited at the beginning, where you have those really low capture rates initially for the amount of sediment. Even though you're capturing 100% of it, if a lot's being left behind on the board, then you're not capturing all of it. So we started breaking this down by mass of fines of sand, silt, and clay. And what we see here on this gentle slope for 2% and one cross-sectional slope and 1% longitudinal slope, the downstream slope, we saw that you had a pretty good mix of your silts and your sands that were bypassing as well as being captured. But for your really gentle slope, all of the fine material is being captured. There's very little bypass there. But for those sands, once those sands start going, they're going. They've got the momentum and they're just shooting by that inlet. And so what's interesting to think about here is if you're thinking about your GSI as a system, or maybe you had one GSI that had multiple inlets, you could shift the PSD, the particle size distribution of the sediments coming in, if you were to put an apron on one inlet, but not on other inlets downstream or upstream. So you could shift where you're collecting most of your sediment or where you're collecting most of your fine sediment within the system. Could you make one of these areas a sacrificial area and just have the others designed to have water? Because you're getting a lot of bypass of flow and larger sediments at this higher cross-sectional slope of 5%, right? Food for thought. So the takeaway from this is that sediment capture of inlet versus bypass increases with bed slope, but the mass of that sediment capture doesn't necessarily increase that way. And the concentrations don't show the exact same patterns. Fines are more easily directed towards those slopes, towards the inlets with mild slopes. And grain sizes that are larger are more connected with that momentum. Now, if you were to move into larger grains, would things change even more? Possibly, because then you're thinking about saltating transport versus transport and suspension. Okay. So finally, we've made our way through two parts of the system, made our way through the watershed. We got into the inlet. Now we're in the GSI. So sediment moving through the GSI. It comes in, things are happening, you're getting advection, and as that advection is occurring, you're also getting dispersion. So as you walk through your GSI, and I know I've done this, and I'd be curious to hear about other people's opinions, especially when you have basins where you have a clear upstream and downstream, you can observe, I've observed, a change in grain size as you walk through that system. When you get into the bowl portion of this, and there's that backwater, everything has time to settle out and deposit. So what does that mean? When you maybe have a little erosion up front, water comes in, it's got all this energy, it starts eroding stuff, so your grain sizes are coarser, and then as you drop things out, as you walk downstream, you have a trend in your particle size distribution. What does that mean for the function of your GSI over time? And this is something that Dr. Kristen Samplord and I have been thinking about for several years, and now our colleagues, Dr. Amanda Hess, Dr. Wisdom Makutu, several of our master students have worked on this project, thinking about this in different ways. And this has been funded by a Growing Greener program through the Pennsylvania Department of Environmental Protection, as well as the PennDOT I-95 Revive project. But we have water coming in with a fairly high velocity, and it hits our GSI surface or our bed, and there's some roughness there. And that's associated with this flow is a shear stress. And that shear stress is going to push around our grain sizes. So we have this combination of erosion and deposition that's happening through the system. As this is happening through the system, some of those finer grains are going to get swept up, suspended into the system, and then we have the coarser grains that are saltating along the bed load. And as this is moving through, those coarser grains are dropping out of movement faster as those finer grains are making their way down till a point where they finally have a place to stop and settle down. And we care about this a lot because we want to know what the TSS in our stormwater is and how those fines especially are able to make their way out of the system or transport through the system. This drives erosion and sedimentation within our GSI, which can affect the stability of this infrastructure, but also has the potential to clog this media over time, right? And this is an example from one of our spots where you can see both erosion and deposition happening in the same GSI. So I'm going to tell you a story about two different GSI. So one of these is located downtown Philadelphia. This is SNPA. It's the lowest one on your map here. And the other, and we're going to be focusing on the lowest portion of this S&P, highlighted in red right here. The other part of this is on Villanova's campus, and this is called the treatment train. And it's a series of connected through weirs that is right next to a parking deck and collecting all that water from a parking garage. So we started modeling this in HECRAS and thinking about how what are the hydraulics and also the sediment transport through these systems. So we collected a whole lot of data, we collected a lot of sediment samples, and we also did a lot of infiltration tests through these systems. So we were able to put all of this into HECRAS and make maps of sediment advection across the surface of these systems. So in surface, the treatment train here at the top, start here. Water is going from point 0 to point 17. All of these points are where we took different soil samples. And here, the cross-sectional bars show where the weirs are located. So this is the water comes in, it hits a weir, and then it hits another weir, and then another weir down here. So you have this flow going along the system, but you also have a series of weirs that the stormwater has to get through, like a stormwater obstacle course. Here at the bottom, we have SMPA, water's going from the top of the screen down below. All of these red marks represent where we take surface samples from across this. And the data that we're using was when this was first built, the first 2 years of its life. And so the vegetation wasn't really dense. It made it a little bit easier for us to model it and to think about it. But this doesn't have weirs. So the water is going again and has a longitudinal flow path, but we're not hitting the same number of weirs here. I will point out this outlet right here in the middle, this is all a backwater zone. So really our hydraulic model works from about here to here. And then once it gets into that backwater, it's all kind of ponding and things are a little bit different. So we did a lot of soil samples, we did a lot of infiltration tests, and then we were ready to start modeling. And what we saw from our soil samples was in the treatment train, the red lines are representing where the weirs are. And what you can see is that that grain size is stepping down every time you go through a weir. You might get some initial erosion right after the weir. The water's got a lot of energy, moving it along. But what we noticed is that the big stuff was getting stuck. It was getting stuck up front, and then it would go into the next one, and then into the next one. So you could visually see that the grain sizes were getting small. And you can see it here too. It's harder to see. It's hard to capture that because soils data is very intricate. And you could take a sample from one part of the GSI and take a sample from right next door, and you're going to get slightly different results if you're along the flow path or not. So you can see that our data is a little bit messy, but it does show this trend of stepping down every time. And now our flow direction has reversed. Just to point that out because it can be a little confusing. We're now going this way. And so this is for the SMPA. And what we saw was the grain size for this first part up to the first outlet right here at B2, we do see this downward trend that's happening with our grain sizes. And even when you take this out of log form for the D50, it's even more pronounced as this is decreasing down. And it matched up with what we observed roughly. So we can see here at the weir, you get a lot of erosion. We have to keep putting things here to make this area stable. In the middle area where you have this inlet coming in at N10, you also have some erosion that occurs, but things start to stabilize a little bit in the grain sizes. And then by the outlet at B2, you can see that it just looks different, right? I could almost take this from different GSI, and you can even visually here see that the grains look a bit different as you're moving through the system, right? So because this is tough for us to capture, we started trying to pair this with our headgrass models. And these are the outlets from the hydraulics of the treatment train, the one on Villanova's campus, and also SMPA. And this is the velocity profiles. And so what you will see here is those weirs, every time you get a weir, you have this peak up in velocity that happens as the water comes down from that weir. You get a little erosion there, and then things start to settle out. And especially once you come up to the upstream end of the next weir, now you have backwater. And so your velocity is slowing down, you're allowing things to settle out, and then you get another peak in the velocity here. Whereas for SMPA, because you don't have those weirs, you have high points of velocity where the inlet's coming in and some erosion that's happening there. But otherwise, your velocity is just decreasing as the water flows over that rough surface and loses energy. And the shear stress shows pretty much the exact same thing. And so unsurprisingly, we see the same trends in our distribution of grain sizes. So here we've got the headgrass model for our treatment train up on top, and then the observed data below. And this is the 1-inch 2-hour storm. You don't see a lot of change here, but when we looked at the 24-hour storm, you did start to see that trend a bit more, the 2-year 24-hour storm. And then we looked at the bed changes for the 1-inch storm. Not a whole lot happened. But when we looked at the 2-year 24-hour storm, this is more similar to what we're observing. And what is hard to capture and isn't shown very clearly, even in the data that I'm showing you here, it's hard to capture this in the field because the field can be really messy, right? And you might be able to observe some of this just walking through this as an engineer, but it's difficult to actually measure this in the field. So we did the same thing with SMPA, same linear trends. The 1-inch 2-hour storm, we didn't see really a lot of trends there. When we looked at the 2-year storm, okay, now this is starting to look more like our data. And then in this case, we had 2 years of data. And so we put that together, and now it's even more pronounced in showing the trend in grain sizes that we started to observe in the field. All right, so why does this matter? Well, remember I mentioned Dr. Kristen Sample-Lord? She's great, and she's got a lot of background in dam filter design and understands that really, really well. And so we started thinking about this idea of graded filters. And with graded filters, you have 2 main criteria, retention and permeability. And so we thought, what if we think about GSI in the same way, right? Because we're concerned about how the sediments are depositing, but really it's about how they're making their way into the soil column and what happens after they've deposited. And so if we know what's depositing where, then can we think about this retention and permeability? And then if particles do have the right to migrate through this, how can they pass through without clogging the media itself? are they fine enough to just make their way through the whole system? So we started applying these criteria to this idea, and we did a lot of tests based on the data that we had collected. And we did these falling head tests. And so we started with two different sediments, one that we would call a compatible sediment for a soil media, and then one that's incompatible. So sorry, an incompatible media and then a compatible media. And so you can see that the compatible media is a well-sorted media. The particle size distribution of this media has got a lot of different stuff going on, different sizes represented, whereas the poorly sorted is just really one size. Both of these meet criteria for GSI, according to most manuals. So we did this falling head test where we put a layer of sediment on top of the media column, and we let it run, and we let it run, and those fine sediments made their way into the system. And then afterwards, we could have the KSAT recover for the compatible version, but for the non-compatible, poorly sorted version, it wasn't recoverable. So we had two different outcomes for this in the falling head test. And then we started thinking, remember back at the beginning where I was talking about particle size and what's coming off of different surfaces? So if you're thinking about what the particle size that's compatible with your media is going to shift depending on what your incoming sediments are. So here we've got based on fine highway sediments, sandy highway sediments, I-95 sediments that we're collecting in Philadelphia, and then parking lot sediments. And so the compatible and incompatible media that we have compatible and incompatible media mapped out here based on your sediments, your sediments are shown in gray and your incompatible shown in navy blue here. And so that incompatible media envelope is shifting depending on what your sediments are. So if you're thinking about designing a GSI that's draining a parking lot, what works versus what might not work for an interstate is going to be a little bit different. Your range of flexibility there is going to shift depending on what's coming off of your system. If you're in a system that's getting a whole lot of finer sediments, perhaps from local construction or something like that, it's affecting the overall system in a different way. When we were looking at these two systems, SMPA and the treatment train, we could clearly see that different types of sediments were being deposited in the upstream versus the downstream end of these. But they were still functioning just fine because it was outside of this envelope of sediment compatibility for these. So it was fine sediments, but it wasn't in a way that's going to be a problem for this. So now it's not a one shoe fits all for soil media when it comes to GSI, right? There's some different things that come into play here. And just building on that a little bit further, this is another SMP from Villanova's campus, and we started thinking about where the fines and the total nitrogen and the phosphates were going for this, and in terms of where things were being deposited. Because this is a different shape, it's more of a bowl shape here. But what we saw was, if you looked at where you had flow inundation, 1.1 and 0.3 get a lot less water than points 2, 5, and 4. And 0.2 really just has water kind of passing through a lot of times. But when we looked at the data for total nitrogen here, you can see the percentage. We saw that in the first 2 inches, where you had standing water, you had higher total nitrogen. And then we started comparing it to the shear stress and the fines and the phosphates, and we saw really similar trends, where the shear stress was really low, where the water wasn't getting to that often. This controlled how we saw the different percentages. And I've color-coded it where green is good and red is bad, but I also have the values here for the fines. You can see that your fines are happening in the bowl where everything's slowing down, your shear stress is really low, not a lot's moving, but you have a lot of water that gets there frequently. And then same with your TP. Things are dropping out right there in the bowl. And where you have water coming in, you have higher velocities and everything's moving, then it's less of a concern and less of a concentration there. You're seeing a lot more erosion, a lot less deposition of fines. So linking together the shear stress and the velocity and what's happening on the surface is where you're getting the deposition of all of this. And then depending on what your soil particle size distribution is, how well these particles and these also nutrients might be able to work their way into the system and work their way through the system potentially. All right. So this is in prep right now. This is the master's work of Zachariah Rashid. And we compared this to our water depth and our water level through time in 4 and 5, which tend to be really had the highest concentrations for everything. That's where you had the deepest water, where water was just sitting there for a long time and had a lot of time to settle out. So in conclusion, all right, we started with the watershed and we said sediment varies a lot across an urban landscape, but there are some ways that we can start to predict this. But we still need a lot of research to understand what an urban sediment is, what it looks like, what you expect to get flowing into your system. However, if we can start thinking about these elements and what urban sediments are, we can use this to our advantage to start planning and thinking about maintenance for different systems and what might work better in one location versus another. And then we talked about inlet design and inlet capture and how you get so much diversity there. And overall, your capture is going to increase as you have a greater cross-sectional slope. And as you get more flow through the system, you have more potential for bypass. However, your fines and your sands don't work the same way. Once your sands get going, you just want to keep going. But the fines are just going with the flow. They're just going to get rerouted into that water, into the inlet, right? So if you're thinking about your PSD and what's coming in and how that might interact with your media, and if you're going to have a high concentration of fines that's maybe poorly sorted versus a well-sorted particle size distribution coming into your GSI, then the slope of those inlets might matter a lot. And finally, we talked about the component of the GSI and how different sediments moving through and advecting and dispersing through a GSI itself. And we can use river models, things that were developed for rivers, to look at this, which is super fun and great. And you can see what you might be able to informally observe a little bit easier in the models than you can collect and measure in the field, because that can be really challenging with just how diverse soil data is, and sometimes how thin those depositional layers can be too. So it makes it hard to capture. All right, this is by far not all prepared by me. This represents a lot of hard work from a whole lot of people, from the V-Cruise team shown here, a really great group of people that I get to work with, Dr. Kristen Sampelord, Dr. Rob Traver, Dr. Amanda Hess, Dr. Bridget Wadzik, Dr. Wisdom Akutu, Carly Letts, and there's just so many people that have contributed to this. This work has been funded by AECOM, the Pennsylvania Department of Environmental Protection, as well as the Pennsylvania Department of Transportation. So with that, I just want to say thank you for listening, and any questions?
Very good. Thank you very much. There we go. So if you are online, please post your questions in the Q&A and they will pop up here for me. Do we have any questions from the in-person audience to get us started? Yep.
Thank you. So many different questions. So I love the conversation about erosion within the GSI, but you also recognize, and we recognize sedimentation into GSI. I'd love to hear your feedback. Have we forgot about pretreatment and the role that has in these practices? Are we going to design our GSI to be the first receiving, or as you said it, the sacrificial GSI, or have we de-emphasized, forgotten, or the role of pretreatment first?
Thank you for that. So considering the role of pre-treatment in GSI, absolutely not. I didn't talk about it a lot today, but this is something that I wonder about a whole lot, because in pre-treatment, if you're capturing a lot of your sediment in pre-treatment, there's been a lot of work around this, especially when you think about underground cisterns. It's impossible to capture everything, right? And so your sediment loads are going down quite a bit. But I also wonder about how you're shifting your PSD, because you're not capturing all of it. You're capturing the big stuff, but depending on what your residence time is, you're probably letting a lot of the fines go through. But are you letting enough of the fines through to be a a problem. And that depends on what you're draining. And those equations we don't quite have yet for the geometry of the pretreatment versus what's going to make its way through the system. We have two larger experiments that are going on right now along I-95 with different types of pretreatment that's been part of the PennDOT work. This is work that Rob Traver and Bridget Wadzik are leading one, where they're trying a new splash pad design for pretreatment. And then we've also been with Kristen Sampelord and Rob and Bridget looking at the design of it's modeled after a step pool system in a stream, so that you would have steps and you would use one step of the GSI as a pretreatment. And this step is pretty big. It's probably the width of this screen, so several 3-4 meters long. And just to force out as much of the sediments, the floatables too, because that's another thing that can often make its way through the system. That's a great question.
So we will take another question from online. Actually, this follows up, it feeds onto that and maybe broadens it a little bit or expands on it a little bit, and thinking about, again, pretreatment and how important is it at capturing fine grain sediment versus coarse grain. Many of our pretreatment are designed for the more coarse stuff, the quickly settling. But how might that difference between coarse sediment, fine sediment, and the total mass as it relates to pretreatment and green stormwater infrastructure?
Yeah, so that's another great question. And I think that it depends on the system. That feels like a really cheap answer, right? But I think if you had a substantial sediment load coming in, let's say you've got a lot happening, and of that sediment load, you're taking out the coarsest part and just allowing the finest part to pass through. That's problematic, right? That's where you're now getting into an incompatible sediment range if you think about the clogging work. But on the other side, you're taking out, if you leave everything in, is it potentially harmful down the road too, and going to result in more maintenance work down the road? So I think it's probably a combination of what your particle size distribution is and what your total sediment load is, and where you're going to reach a threshold of concern, and balancing between those two. But exactly where that is, we don't really know. And I think a lot of this depends on the geometry of the pre-treatment and having something that's big enough and allows enough residence time for things to settle out and happen. Because what we saw in the last GSI that I showed you, this is a nice bowl, but you can clearly see how fines and nutrients and phosphates all are being deposited in the center of that bowl because they're given enough time to, right? And this is what we're hoping to find out from the STEP and the splash pad program. Yeah.
Great. I think I saw, yep, question up in the back.
Virginia, you started the presentation with a kind of a discussion about how the sampling methodology and the sampling tools could really affect the data. And I guess what I expected to hear going into the rest of it was that you had that in mind and that your sampling methodology doesn't suffer from that. But maybe you could, I guess, confirm that. And then, how do you think about that in terms of the data that you're presenting, and just general recommendations for, trying to bridge that gap?
Yeah. Thank you. So this was the question. I'm pretty sure everybody online can hear it, but I'm just going to repeat it just in case, just to make sure I understand, right? So how to consider the sampling method and the analytical method when looking at sediment data, right? So what we did was we saw a few obvious outliers in the analytical method in the grab samples, and not in the grab samples, but in when we were looking at the analytical method and the sampling type, and those we removed from our analysis because it was too far away from what we were trying to say. So we tried to keep within the range of things that were not statistically significant. There was no statistical significance in the differences between them. And so we tried to stay there, but then of course it narrows down what we're actually able to use. So what I learned from this, and what I'll take going forward, is just certainly to be aware of the method. And if the sediment data is only auto-sampler data, I know that this isn't going to have much coarse material in it. It's just not what's being collected. I'm limited by the feasibility of the grain sizes there. When I'm looking at a grab sample, I might get something that's more representative, but another element of this that I didn't really get into is this a first flush sample versus is this a sample that's being taken at regular intervals through the system? We tried to stick with first flush samples as much as possible, just so that it could be across the board, but sometimes that's not told to you. So I would even say in reports and just for the transparency and fair data application, the findability, accessibility, interoperability, and reusability practices, just to report as much of that metadata as possible so that it can be reused in a way in the future that makes sense. Because it's really hard to tease out sediment data. There's not a ton there, and it varies so much depending on if you're getting the full column of the flow or the first flush versus 5 minutes into the storm. It's going to be completely different numbers. Yeah.
We'll take another question from online. So this question actually comes from Mike. The last question was from Brett, actually. This question comes from Mike. When thinking in terms of the system, should we also be bringing in P2 and source control into the equation? For example, coupling specific lawn and leaf capture practices with preferred and desirable GSI, such as rain gardens.
Absolutely. I think if that's feasible, 100%. And I think that's an interesting idea of in Philadelphia, they've just started back a street cleaning program, right? And of course, this is going to change what's going into your GSI and the grain sizes that are going into your GSI. But I think thinking of how these processes interact and what it means when they do interact is an interesting thing. And quite honestly, I don't know a whole lot about how some of these upstream mitigative actions, let's say, would impact what's actually coming into your system too. But I imagine that would shift your practices and the success of your practice over time. For me, it was really interesting in the work of Kate Homit. It's interesting to see the impact of the litter index on this because it really changed things. This is a open data source provided by the city of Philadelphia, and how exactly they come up with a litter index, I'm not entirely sure off the. I'd have to refresh my memory on that one, but it was very impactful in the results that we saw. Yeah.
We'll take a question from the in-person audience right up front.
So one of the leading negative impacts of concern is clogging and ponding. If your work is leading toward being able to predict where that's going to happen, and I'm wondering whether you think it's possible or worth the trouble to develop a method of automatically, remote sensing, detecting ponding in these GSI features so that a maintenance department that's got hundreds of these things to deal with can know where to go when they need to go there.
This is such a great question, and I'm sure my colleagues that might be listening online are going to be like, she planted that one, but because this is right up my alley. So right now, Dr. Garrett Clayton, he's a mechanical engineer. He's into robotics. We've been talking a lot about sensors, and he's got a PhD student that's working on this question about what can we get out of different types of sensors to alert us to a problem, because the 2-year storm reflects how grain sizes are moving overall across the GSI, right? But even these small storms are moving the fines. And you can have a really intense storm. And what we saw in Philadelphia in August, we had a really intense rainstorm that just moved a lot of sediment. And that's when you need to go out and maintain. But how are you alerted to those thresholds? So there's some recent advancement in multispectral imaging that we're really excited about, that you can pull out turbidity from multispectral imaging. So if you had something that was just there, could you look at the inflows and say, ooh, this is turbid. Somebody get out there and we need to fix this pretty soon, right? In addition to that, could you also have, and I'm going to use this term again, maybe not a sacrificial inlet, but a sacrificial portion, where you know that the water will slowly move through a lot of the GSI. And then in this part, this is where I expect a lot of my problem sediments to be over time. And so maybe that instead of maintaining the entire system every time, you're maintaining 10%. And that was also the idea behind the step pools, is that you maintain that first step, and maybe even every so often you shovel it out and put some more soil in if you have to. Hopefully not, but if something's going to fail, it's going to be limited instead of the entire system. And so I think you could think about this in terms of, like designing inlets to have inlets that are receiving different types of sediment loads, but also in your GSI itself, putting weirs in or using the system to concentrate where you're getting potential problems.
Call it a four-bit. We'll have the negative conversation.
Yeah. Yeah, that's a better way to think about it. Yeah.
We'll take one more question online and then we'll take our break before our panel. So this question actually comes from Paula, and the question is, regarding the sediment characterization, did you look at the time of year that the samples were collected? Besides vegetation inputs, road maintenance, road construction, and other seasonal activities, these might impact the type of sediment collected, grain size, those kind of things.
Yeah, that's a great question, Paula. So that was our dream. That was our hope. And I mentioned it a little bit earlier. I think the freeze-thaw cycles come into play. What's happening here in Minneapolis is going to be different than Philadelphia. It's yours is, and your snow melt cycles, right? It's snowy and freezing, and then in the spring it warms up. Whereas in Philadelphia, it's freezing, it's warm, and it's freezing, and then everything melts. And so it's this more up and down. And how does that affect how much sediment you're getting over time? It's probably doing something, right? Unfortunately, for a lot of the data that we were able to glean out of the literature, and we searched as much as we can, we looked at the International BMP database, that metadata just isn't always available. And it wasn't available enough for us to be able to say anything of statistical significance. So I think, Holly, you're absolutely right. That's got to play into it. How much organics in this? What does the sediment look like? What's your leaf litter index impacting this? It's got to be part of it, but it wasn't part of the story that we were able to tell, just lack of data. But one day, that's the dream. Yeah.
We would always want to know more, right? We always want to know more. So, well, help me thank Virginia for giving us the keynote talk today.
Pleasure.
Thank you. For those of you online and in the room, we're going to take a 5-minute break. We're going to transition to our panel discussion. Please join us in just a few minutes. Grab drinks and coffee. Thank you. Our first panelist is Gregg Thompson, who is a watershed specialist at the city of Eagan. Gregg, from your experience and perspective, how do you relate to our topic today?
So I've been working with bioretention for quite a while, and then have just been working on a lot of sediment maintenance and the maintenance of the systems, and involved with regulatory and planning and just a lot of maintenance, but many years of that, and trying to understand what's going on and what's effective for these systems to function correctly for a long period of time.
That's excellent. Thank you, Gregg. Our next panelist is Jessica Wilson, who's a water resources manager at the city of Edina. Jessica, from your experience and perspective, how do you relate to today's topic?
Hi, everyone. So a part of my job is the provision of clean water services, clean water in the city. And a section of that involves the inspection and maintenance of these stormwater infrastructure assets on the public side and the private side. So just trying to kind of plan, or understand what we have and the condition they're in, and then plan for the reinvestment in those. And then on the private side, doing some inspections and letting people know the condition of those things. And then they come and say, well, what do you want me to do about it? And we're kind of forming up those answers for them right now so that everyone can keep those devices and infrastructure working in proper working order to do what they were designed to do.
That's fabulous. Thank you. Our next panelist is Ab Fleming, who is the Sustainable Landcare Manager and lead trainer at Metro Blooms. Ab, from your perspective and experience, how do you relate to today's topic?
Thank you, Andy, and thank you all for having me here. I'm once again going to bring up the maintenance. So during the growing season, I lead a crew in the field, maintaining a number of about 50 to 60 BMPs around the Twin Cities, mainly in Minneapolis, many of which are rain gardens, bioswales, vegetated structures. And then I also perform inspections on them and report to the city of Minneapolis. I do stormwater reporting about functionality. And so just looking closely at these systems, not only observing how they change throughout the growing season, but then also in the last few years that I've been working with them. So thank you.
Very good. Very good. Thank you very much, Ab. I'm not going to ask for Virginia's perspective because she gave the keynote and set the stage for our talk today. I'm going to take our first question actually from online. This came in during the keynote presentation, but I felt it's very applicable to our panel. And the question is, typically we think about first flush, right? That first dose of runoff carrying the most pollutants. So the question is, does some of this data or some of your experiences confirm that or contradict this concept of first flush? Is that a real thing? Anybody can start.
Sure. From our data, it certainly looks like first flush is a real thing. And when the number of dry days, even before you have a rain event that happens. So if you have a really long dry period and then this wet event, you've had a lot of time for things to build up on the surface and then get all flushed and washed off. And so that's what we're seeing in our data, that this first flush event, if you're looking at the first, even just the first couple minutes of a storm, because a lot of these drainage areas coming into GSI are really small. And so that first flush happens really quickly in the system.
I would say my response is when I think of first flush, one of the limiting factors I feel on my crew is the timing. We don't always visit all of our sites immediately after a large rain event. You know, it's all scheduled out and we're visiting our sites maybe once a month throughout the season. But when I think of first flush, I think about right away in spring, especially here in Minnesota, how that relates. We definitely make a point to visit all of our systems and be cleaning out the inlets and removing a lot of that larger debris, a lot of leaf litter, a lot of trash. Right away to make sure the system is open and ready for the rest of the season. So that's how I would relate to that.
I think one of the challenges too is the accumulation of material doesn't really sync with the way we've programmed our maintenance or inspection. So that's typically one time it gets inspected, unless you have neighbors who are helping you with those informal inspections, right? And letting you know. And then we program maintenance. It's usually when there's, you know, sediment has built up to a certain amount. If I bother my utility superintendent when there's a small amount of material, he's going to say, I've got bigger fish to fry, I've got other things. And sometimes we joke about how things can be like self-cleaning, right? Well, in that next big storm, it'll be, you know, that it won't be there in that pre-treatment or in that forebay anymore. So I think that's kind of one of the challenges is, does stormwater maintenance rise to the priority on a public works workflow to get out after those smaller events? Who's cracked the code on that? Tell me.
Who has the silver bullet, right?
And yeah, we see that first flush and the intensity of that event. If we see some event coming in the forecast a ways out, then we work with our streets department and try to get through and sweep some areas, some high priority areas before we have to deal with that within the system. We've been doing a lot of retrofitting to get in better pre-treatment devices into the ones that were built before pre-treatment was, you know, part of the mix of that. But we're just trying to up our frequency too for revisiting the pre-treatment systems to keep those cleaned out. So we're not dealing with all that coarse material in there, but yeah.
It's tough, right? All right, let's take a question from our audience.
So I'm clearly fascinated with this automation and inspection thing, but a couple comments that were made. One is what we're seeing in Minnesota because of climate change is not more annual precipitation, it's longer dry periods and more of our rainfall coming in intense storms, otherwise known as the storms that cause the problems. Then there's these questions of inspection frequency as well. So there's kind of two questions here. One is we now have pretty inexpensive camera devices hooked up to solar power, so they don't have to be wired to anything. And I'm wondering whether those would be useful to put in place for ponding locations, but also pre-treatment, so that you can actually do a visual inspection really quickly on 100 different places right after an intense storm. doing all remote video stuff. The other, though, was the comments you made, Jessica, about volunteers to help with inspection. We have the Adopt a Drain program in Minnesota, which is something you all might want to look at in Pennsylvania as well. But you might actually be able to enlist the folks that are already signed up for Adopt a Drain to assist in GSI, really simple GSI inspection. That could be a really nice linkage. So those are the two questions.
First of all, I just want to say that I love the idea of getting people involved, even just for the interest of it. You know what I mean? Start to like inform people of what these systems are and the value they have. And personally, that's one of my favorite things about my job is showing up to a site and just seeing how it functions in the greater landscape and seeing that it's working. Or even if you show up and there is standing water, it's like, it worked, you know, that's super cool. The majority of the time we don't see that, especially in the times of severe drought. We're dealing with a lot of, you know, like plant die off and that kind of thing. And then exactly. Yeah. Yeah. And then in terms of cameras, I mean, I think that could be a great idea. Again, I'm just going to say, I would also be very interested to be able to see them like actually in action. But it would be great to have a way to inspect them remotely rather than have to go to all these different sites. And a lot of times I find myself doing inspections while I'm actually on the ground doing maintenance with my crew. And I don't, you know, have that freedom to sort of sometimes just do inspections when I feel like the timing might be better or after a rain event, that kind of thing.
I like that idea of prioritizing where you should look. Like maybe there's an alert that says, you know, based on all these predictive things about the weather pattern that we're in and all of these things, or the drainage area, that, hey, you should go take a look at this one. And then go out and take a look. I think with gray infrastructure, we've gotten really good at that preventative maintenance, right? Go out and grout the manholes, and that can extend the life of your, you know, grout the rings, right? Can extend the life of that thing for a long time. That's an obvious thing to do, but we don't have that really for the green infrastructure, green stormwater infrastructure yet to say, hey, go out and, you know, check out the sediment in this particular area and do some stuff here before it just totally fails. And then, you know, then I think you're dealing with some other kind of perspective or perception things, right? Where people are like, why'd you let that get to that point where it's totally in a failure mode? And I think some of the pros and cons of green stormwater infrastructure, it's very visible, which is good. But then when it fails, that's also very visible. So is there any things you can do kind of to those interventions to extend the life that are, you know, maybe 10% of that 4-bay area that you're maintaining?
Yeah, and as far as with the technology, I'd be totally up for that, of anything that we could do that would prevent not wasted trips, but help us prioritize. We do have sort of a network of volunteers or of residents that will notify us of issues to be taken care of pretty quickly. And then we just know of our bioretention practices or the filter benches that once we get a half-inch event, we know we got to get on that right at that point or try to do maintenance ahead of that. But yeah, it's with volunteer outreach, that's not super consistent.
I'm going on the technology side too. I think this idea of where to maintain when, it's a huge challenge, but also with the technology side, it's such a big opportunity. And I think cameras as well as LiDAR, even thinking about maybe a stationary LiDAR puck, because the prices on those they're getting more and more obtainable. And even if you could have something that's just there and looking at water depth changes, or as well as, you know, like when your bed's changing or when you're getting a major blowout from erosion, like that would ping in LiDAR. You could set up a program to do that. And that's something Garrett Clayton and I have been talking about for a while, about doing some of that. Another thing that people are starting to gain some traction. And of course, there's a lot of rules and regulations around this that are still being figured out, but drones. And what if you could just have a little doghouse for a drone? It just runs through. The PennDOT project that I have talked about, the I-95 Revive project, that's going to have around somewhere 80 to 90 GSI altogether. That's a lot to inspect for one. That's just one project. And then when you think about the city scale, you know, that's so much to keep track of. And so, you know, there's a lot of opportunity there. It's just kind of figuring out some of the details.
And you could do so many things with that too, where you're looking at programming GSI, but also like, okay, there's a clog at this inlet and it's causing street flooding, and like, get out there now. You could have so many things that you're layering in with that.
I actually want to, we have questions both online and in the audience, but I want to tack on to something that was said both in the first response to the first question and this response. And it's related to, well, maybe I'll comment on maintenance first. Real-time controls, we use real-time controls on some of our practices to operate, right? So this concept of using technology and sensors and information to help us maintain or identify failures, right? We could have sensors that tell us when things are clogged or water's backed up, et cetera, et cetera. I think that's something people are thinking about. I haven't seen it implemented yet. So maybe that's kind of the next frontier. But the question I want to ask is actually related to, let's call it unsolicited volunteer inspections. Okay. I recognize that these come in, right? But we also have our priorities and we know what we want to maintain. So how do you balance that? How do you balance what you get from residents, homeowners, landowners versus what we prioritize in our stormwater infrastructure and management?
I guess for us, we have our priority water bodies, our lakes that we're trying to protect. And so then those rise to the top of anything within the direct drainage area of that we're hopping on right away. But yeah, we have to triage this to try to be more efficient with our time. We are adding this year some full-time equivalent hours for some of our other streets departments to start picking up they're adding some people to start helping out with some of our maintenance, because otherwise it has been just two of us that cover the city, and then we get our summer interns after, for a limited period of time. But
I don't have a great answer. I have to be honest, I don't really deal with a lot of volunteer inspectors. So at this point, yeah.
So let's take a question from online. So this actually relates to, it does talk about maintenance and frequency, but it gets to the particle size distribution. So the question is, how does the increased capture of fine sediment versus coarse sediment change our green stormwater infrastructure maintenance? Not only the practices, what we do, but the frequency.
Again, I don't know if I have a great answer for that, to be honest. I mean, a lot of the maintenance that I'm focused on, to be fully transparent, is the vegetation. We're doing a lot of plant management, a lot of replanting, or just management of bare soils. That's one thing I've been thinking about in relation to this talk, is just, even just on a visual surface level, how do I sort of observe and inspect like the sedimentation in a practice? I can't always tell, especially when it's heavily vegetated and there's a lot of plant cover. Like, unless there's like a large sort of like, unless we had erosion that caused a large pile of like sands and stuff that I can just see, I don't really see a lot of what's happening with the sediment other than what's in the pre-treatment structure when I'm opening and cleaning it out with a shovel. So
I think with that pre-treatment forebay with the sediment, usually it's visually like, right, 50% or more full. And when it's big particles, that I feel like triggers people to say, I need to do maintenance here. But if you had a bunch of fines and it's like, it's like, doesn't take up 50% of that forebay area, people might say, this can wait, even though the risk might be higher for clogging. So I think what I've learned today is like, that might be a higher priority of those more, fines. Maybe it's not, you don't wait till the 50% threshold to get out there and do that.
Yep. And that would be, with us, we have a lot of, the rain guardian turrets. And so the filter, that whole thing functions a lot better if that screen is maintained real frequently and through power washing or something, because your fines can get in and plug it and just make it all not necessarily fail, but it's not going to be able to store much of anything. So we do try to do frequent, thorough cleanings on those, even if it's not full, to try to get to those fines, that very fine little muck that can develop in the bottom of that.
I think it is a really hard thing to observe. Sometimes you can even see it like in vegetated areas, you can see the fine dust on the leaves and like that. And we have such a nice set of observations that go with this, and we can tease out some of the things that we want to see, but it's hard to soil speed is hard to tease things out sometimes. And so I think that if you can model and try to predict, that might be helpful too. And from the standpoint of thinking about a whole bunch of GSI everywhere, if you had areas that you thought might be more subject to different to fines, then you could maybe focus on those areas instead of trying to do the whole everything everywhere.
So we will take a question from our audience here.
I'm thinking back to the presentation, Virginia, you put on the screen that cross slope and longitudinal slope model, and the graphs that came out of that, and I think we haven't really had some conversation about yet. If I were to put the question to the local panelists, where did your mind go when you saw that data up on the screen? Is there a piece of operational guidance or design guidance that made you think of right away? And then maybe we could get Virginia's reaction to that, because I'm sure her team in Virginia has thought a lot about it, but design and operational guidance based on what you were seeing there.
My first thought was, I wonder if this is part of like the design guidance in the stormwater manual.
Yeah.
'Cause I don't do any design or review of design, so it's hard to know. But thanks for calling. Now I get to say that to the group that I don't know. But I was thinking, it felt like, oh, this is something that I could see like on the public side, where you're being really thoughtful about the maintenance, about how do I make this really simple going forward. I think on the private side, it's usually how do I meet the requirement, and I'm guessing, people can correct me, that it's more based on just like watershed and drainage and water volume, right? I'm just going to design this thing for water to get in, but you're not necessarily thinking about, is this thing going to be easy to clean in the future? I'm not sure. So yeah, I don't know if I think there might be maybe on the public side a little bit more of that early adopter, just because you're thinking more you have your own public works that might be in the room when you're designing that. But I don't know if that same thing is happening on the private side. I really don't know.
And my initial thought was, I need to check our details just to make sure, on what's the slopes noted on that, but that's usually
And it feels like kind of a sophistication of your design. Okay, so far we've just been like, how big and how deep does it need to be? But I think as you get more and more sophisticated in stormwater management, now it's really awesome that we're starting to be like, okay, what's 1% or 5% slope? How does that change it? I feel like that's just kind of the sophistication of the whole, industry.
So my thinking about this is really started with thinking about, do you need an apron on your inlet or not? And you can't really control the slopes of your roads. We used 1% and 2%, thinking that starting with 2% just being like the crowning of the road that might already be there, and 5% is if you put an apron on it, essentially, and how that affects what your capture is. And so is the apron worth it? And it depends on what you're trying to do, because it definitely changes your capture efficiency of your flow, and it certainly changes the capture efficiency of your sediments too. And so, and the other thing that I thought is that maybe this is an area where you're not getting enough water in your system. You're getting a lot of bypass. Okay, well, I can look at this and see if I'm getting these more intense rainfall events, that the GPM, just the flow rates going past this are going to result in more bypass over time, more fines and course getting separated out, but maybe cleaning off my surfaces when these big rain events do happen at the same time, because I have a high enough shear stress. But if I'm getting a lot of this bypass, then perhaps like a really simple fix is just putting a patch right there, right, to rework the water. And so in cases where you're seeing like, okay, I understand I'm getting a lot of bypass here. It's not the drainage, something's happening in the drainage area. It's just the flow has so much momentum, it's just not making its way in. So you could have like a simple fix instead of having to rethink this on a larger scale. So those were the two main areas of application that I thought this work paired into, of deciding whether or not to put in aprons, deciding why this might be resulting in not getting enough flow at certain times when you expect to have more flow, and how you might be able to just put in a simple fix there to get around it.
So I'm gonna follow on with that, because the concept, part of the question is design. How does it feed back to design? And we see in many of these conferences, there could be tracks saying designing with maintenance in mind. So as Jessica said, right, we'll often design for what we need to treat, what we need to capture, what we might need to infiltrate, et cetera. But that feedback loop of what do we see in our maintenance activities, and how does that feed back into improving our design to make either maintenance easier or more accessible, think like that. So is there any things you've done in recent years in how you go back to design, or maybe talk to designers or ask questions to designers that have come out of some of the maintenance? Or if you've seen things and you haven't asked yet, what would you say to designers to say, hey, this is something we're seeing in our maintenance activities. Is there something we can do better in design?
Requiring pretreatment on everything.
That's what I was gonna say.
We do, yeah, in some cases, redundant pretreatments for underground systems, especially. Trying to make and thinking about where these areas, adding splash pads, you know, in areas where we were trying to do like a turf filter or something right after some pretreatment, or something, just something that is just easier to clean. Because then in a lot of cases, it's me and a coworker with flat shovels out there cleaning stuff and rakes and all that stuff. But yeah.
Other thoughts?
I don't know. That was my gut reaction as well, was we've already highlighted the importance of pretreatment, but it just makes a huge difference in capturing both the larger debris and then also the sands and the fines at times. And it's just so convenient to be able to scoop it out with that flash shovel. So.
And in combination with more street sweeping, which everybody likes and wants. And even our, you know, streets and utilities people are like, good, then it doesn't clog in a rain event. And I'm out there just trying to get, you know, the street clear of water or something like that. So I think that's another angle.
I'll just highlight that for anybody that's online and maybe outside of Minnesota. Minnesota has actually in recent years done a lot of work at increasing the amount of street sweeping, because we are seeing so much positive benefit, and the cost effectiveness of street sweeping and pollution prevention for sure save a lot on the maintenance and on the primary treatments. So let's take another question from online. This question comes from Paula. And this, I'll kind of broaden it for the whole panel. So the BMPs that are being studied and maintained so for example, specifically for Virginia, in the data that you collected, were those BMPs that you measured, were they maintained throughout the course of the study? And were you able to track that and look at how that might affect performance? And this actually kind of gets to something Ab said about vegetation. Could we adjust media or plantings in the downstream areas of GSI so that infiltration is more easily restored through regular maintenance, like raking out the sediment frequently, other things we might do? Go ahead.
Yeah, I absolutely think that. So you could think about these. I presented two GSI, right? And one was just a linear system, and one was a series of systems and links. And you could certainly think about that. One of the challenges when you're being really specific about the grain sizes that are being used, sometimes the actual construction of that can be really can be challenging, like to get exactly what you want in there. You know, you can have the perfect design, but it also has to be constructed in the same way for you to get the results that you're looking for. So I think you could absolutely design a system and have a system where you're designing to reduce maintenance for the system, but maybe have one area where you are expecting there to be more work. And so maybe you're going to that area more frequently. But I think that you could certainly shift around your grain sizes of the media that you're using to really try to optimize what's happening, and also think about your vegetation that way too.
we've used this word sacrificial a couple times today, but I wonder if there's a way to kind of overlap those where you'd have to kind of repair the soil because of a siltation, but also like you have a lot of chloride load, especially in these urban places where the plants are probably not going to do great. So can you kind of like do those overlap, or are they in different places so that you could also like further reduce that footprint of like, all right, this is an area where we're going to have to continually repair and replace and enhance?
That's a great question. And especially when it comes to vegetation establishment. Like if you're fully, digging out a portion of your BMP and having to reconstruct it every time, you're starting at base one, in theory, with small plants again that aren't, as established and resilient. So, yeah.
Let's take another question. Let's take a question from our in-person audience.
So sediment maintenance is inherently a reactive process just due to sediment being loaded by the urban environment. Is anyone thinking about ways that we could be more proactive in preventing either the creation of sediment or that sediment getting to green infrastructure in the first place?
Yeah, so in the city, then my coworkers involved with construction site stormwater management. And so just really sticking on those, looking for any sites that are leaching out fine sediments. We're trying to encourage or really require on development sites for them for their green space areas. Any soils that are disturbed that are to be revegetated then have to be deep loosened and amended with compost to try to recreate an actual sponge in the green space, because we see in historically a lot of areas that were graded and covered with turf grass or green concrete, we call it, that just sheds a lot of water and a lot of sediment comes along with that too. So we're just, looking for all those sources to trim it down so we don't get as much of that load into the bioretention or whatever facility.
Yeah, I was going to say, I don't know if I have a great answer for that. I have even another question is, also a lot of the sites that we maintain, specifically at public schools grounds in Minneapolis, they have, the BMP or the rain garden is right next to the recess field, which is grass. And then, these last couple seasons of severe drought, a lot of that grass has died, not to mention the foot traffic of children being out there every single day. And it just becomes dirt, you know what I mean? Like our rain gardens are surrounded by a lot of dirt patches, which is ultimately washing into the system. Not even just through the inlet, but, through all the edges. So I'd be curious, what can you put in that area other than turf grass that children are going to play on, I don't have an answer.
Anybody else have an answer?
I don't have a complete answer. I have an incomplete answer.
Okay.
I think
Okay, that's okay.
part of this is maybe also just maybe it's another question, but understanding the time. How long do you have to get out there and clean it, right? Like, so if you have something that's starting to flow in, what's your threshold? You have a construction site, right? And you get a plug of fine sediments coming into your system and it's deposited. How long before that starts to make its way into the soil column? And if you knew that, then maybe this isn't really where you can be preventative, but you can just be proactive enough that you're reacting before you have to, before something starts to fail. And the fines can be a real problem because once they're in there, there's not really anything you can do other than just completely take out the soil that has the fines in it. So maybe understanding the timing side of that would be helpful also. And like, how much of an emergency is this? Do I have a month? Do I have a week? It probably depends on how many storms are going to happen too, and help those fines on their way. Yeah.
Other thoughts?
So we do try to be very proactive on the construction site management of doing a lot of enforcement even during the drought periods, and the contractors really try to push back on that, but it's to try to be preventative on, we don't want to have to react after it's leaking out. Yeah, chocolate milk. Yeah.
I like to think of it as what level of risk are you assuming, right? It's like if you don't do maintenance, as time marches on, you're essentially assuming more and more risk, getting closer and closer to failure and possibly causing bigger problems than what you have right now, right? So any other comments on that question or thoughts? All right, let's take another question right here.
Thank you. So two design questions. One is on inlets and bypass. An interesting variable seems to be potentially the inlet width. So they're standard, but if they were a good bit wider, that might change their performance significantly. It seems like a variable worth looking at, and it either could be wider or you simply double a standard, a standard installation at an inlet. The other question, though, is regarding weirs. So you talked about that a good bit in your presentation, and they influence performance. You could use a weir to create this equivalent of a forebay. The forebay could be the equivalent of a pre-treatment system that wasn't put in originally, and now you really can't go in and build it. The question is there potential in using weirs as a retrofit technique? And if there is, would the cities in particular be interested and willing to consider putting in weirs in existing GSI BMPs?
I could just mention how we have started retrofitting that into, or it's probably been 6 or 7 years ago, into some swale situations that we would do permeable weirs. And then on the first one, we did on the first because of coarse sediment, then we concreted that to make a nice flat surface to be able to go in and scrape it out. But yeah, we've retrofitted on some.
It's a great idea. It seems like a really low cost way to simplify that going forward. And you could kind of just quickly evaluate each of those. It wouldn't necessarily have to be over designed, right? Just to have something to. Right.
Yeah. Yeah, I think absolutely. It would, every GSI is a special snowflake. And so it would kind of depend on the geometric layout, but that geometry really controls how the sediment's moving through. That's been the fun thing about thinking about sediment is this combination of the land surface and what's coming in from the watershed and the hydraulics all reflected in that together. And so I think that seems like something that could be really obtainable in a lot of different ways. To answer your first question about the width, we did some experiments on that, Ampma et al., as well as Hussein et al. We've got 2 papers out that in irrigation and drainage, and both of them are in irrigation and drainage, that I'd be happy to share too, where we played with a lot of different variables, a lot of different widths, compared it to the current design equations and what we saw with headgrass and because we did the physical models. What I didn't get in today is that we also paired this with headgrass so that we could go even beyond what the flow rates of our flume are that we're running the experiment on. So we've started that on the hydraulics side, but we haven't gotten there yet on the sediment side. So we do have the headgrass model that's working for the sediment, but we haven't gone to higher flow rates or different widths. We've also done some experiments with the sharp nose width versus the rounded. The sharp nose inlet versus the rounded inlet. And so those are directions that we're hoping to go in. The other side that we're looking to move towards too is thinking about how water flows around grates and bypasses around grates, because we also see sometimes your grate's 6 inches from the barrier of a wall, right? And sometimes it's right up next to it. And so how much bypass do you get in that area? And what we've observed is that can be pretty substantial. And so those are the 2 areas that we're moving into next. Yeah.
I'm actually maybe hearing or maybe more inferring 2 things out of this. First, we've heard pretreatment seems to be really important. So like doubling the width, doubling the inlet might also allow us to make our pretreatment bigger, right? And then maybe that, again, eases maintenance, maybe reduces that frequency, because if it's bigger, it has more capacity to hold more. because we're already strapped for personnel to be able to actually maintain these things as often as we'd like to. But also in a retrofit situation, if you don't have pretreatment and you want to use weirs or some other means to create those conditions where we can capture that material in a specific location that's easier to maintain than the whole basin. It sounds like those are a couple ways that we can impact design, thinking about design and retrofit and new construction type possibilities. So that's what I'm hearing. Let's take another question. We'll go back online. And the next question we're going to take is going to be thinking about uncertainty and variability. So that kind of came up not only in the data, but I'm sure it shows up in the real world. But I'm gonna broaden the question a little bit beyond what was asked specifically. So you can comment on uncertainty and variability, how that kind of impacts in the decisions we're making. But I also want to ask more specifically, when you're thinking about maintenance, does it oftentimes boil down to really simple answers, very simple action steps that, we talked about inspections a little bit. Does it really, even though there is a lot of variability and uncertainty in some of these things, does what we actually do to improve the performance through maintenance really boil down to simple things? And maybe that variability and uncertainty doesn't have a big impact on the decisions we make. Do you see what I'm saying? What would you comment on that?
Yes, simple steps.
What makes simple steps so valuable?
It's just simple, frequent steps. It's the frequency that it's hard for us, but it is a lot of simple steps, but it just is able to stay ahead of a problem. I don't know.
My response to that would be, even though there is uncertainty and variability, we're pretty much doing the same stuff at most of the sites we visit. We're checking the inlet for sediment or the pretreatment structure. We're picking up trash and debris. We're weeding. We may be putting down mulch. So yeah, I don't know if I have a great big picture answer to the simplicity. I mean, we're often doing the same thing. And something that we are trying to be more proactive about, and my company is just being more proactive with some of the things we're doing. I guess, for instance, what I mean is making a point to reach out to our clients and say, we really think we could revegetate. We could install some mulch. I mean, some of the limiting factors are we show up, we're doing maintenance. There's not always written into the maintenance, funds to be adding plants or adding mulch or restructuring a portion that has begun to fail. So yeah, being a little bit more proactive in having that kind of interaction with who we're working with.
Other thoughts? So I'm going to ask this question. This is one of our prepared questions. I want to ask more specifically about lessons learned. So what kind of lessons learned have you experienced that you would like to share with our audience today? What kind of things have you learned that might benefit when we think about sediment, when we think about maintenance and management of these systems beyond what we've already talked about, if anything?
It's a lot simpler and cheaper to keep things working that are already working than it is to let them fail and then come back and repair those things, not just from even a capital side, but public perception side and the value that those things are providing. So keeping it working, there's a lot of value in inspecting and doing those kind of preventative maintenance steps.
Mm-hmm.
And putting the funding in for those preventative maintenance steps. Another thing that I sort of forgot that we've been really ramping up within our capital improvements plan of a line item for that really covers maintenance, in a way for contracted maintenance, because it's too much for just a couple of us. And so we have been over the years picking up getting more of our public BMPs on contracted maintenance to take the load off of us. Cities need to put more money into that maintenance side.
Mm-hmm.
I think even on the, non-city owned things, getting eyes on those things,
Yes. Yep.
especially when they're in those often in those commercial places where the land is really impervious, and cities rely on all of these practices that are happening on private property to work if you want to actually achieve your TMDL
Yes.
reduction. So I think my advice would be to get a handle on, your citywide assets, those that you own and operate and maintain, and those that you don't, at least so you have a feel for like, what's, how is it going here in this community or this drainage area to this water body that we care about? And then I think the other bit of advice is just start doing those inspections and maintenance, even if you don't have a fully, even if there is some uncertainty on like, do we have everything mapped? Do we know what we should do here? You just kind of got to start with what you have.
Mhm. This is kind of a response to the lack of staffing that we all struggle with, but a lesson that I've learned is that young people are very interested in this. Something that we do at Metro Blooms is the Sustainable Landcare Training Program, in which we have youth and young adults come out to sites, and we just have a collective conversation and some education about what we're looking at, how it functions, what the different plants are, maybe insects we're seeing. And we find that a lot of people are super interested in what's going on. So a lesson learned might just be, being educational in what these systems are and having more of like a community conversation around it. Mm-hmm.
Yeah, for me, maybe I don't want to be too negative, but I feel like it's been exciting to see how so many cities of so many different scales have taken on these programs and how these continue to grow. And our cities are growing. These programs are going to continue to grow. They're going to get bigger. We're putting in more and more systems. And so the maintenance responsibilities are just going to get bigger and bigger and bigger. And this is still a relatively young style of infrastructure when we're thinking about the grand scheme of things, right? So what is this going to look like in 20 years? And what is this going to look like in 50 years? Because we know that the systems have to get bigger. The maintenance burden of this is going to be bigger. And so, well, that feels really heavy, right? But at the same time, there's a lot of lessons learned, a lot of experience that has been able to teach us the positive directions going forward, and thinking about simple steps, thinking about frequency, that you can't leave these, the value and importance of maintaining this and keeping it going, and then what are some solutions and how can we get around it? And conversations like this, where you're linking what's going on in the field and you're linking what's going on in research, so that you can pair those two things together, because this is going to be a big obstacle. And how do you get around some of this? I think that having communities like what you've created is a really important thing, just so that we can continue to advance this, because it's not a small thing to do, right? What you're making happen. And so I think it's exciting to be part of this, to think about how we can get around this big obstacle. And there's a lot of advancements that are setting the stage to do that, which is a great thing. Yeah.
Other questions for our panelists? I can take another one online unless we have one in the room.
Can I respond to
Yeah, you
something?
can. Add, please.
So I think when you think about like what all the services that a city provides, and we have like our water utility and our sewer utility, and then down here on the floor is our stormwater utility, as far as like, what people are like understand about the value of those utilities and how we fund them and resource them. And even on a professional side, so we have professionals that have degrees in water delivery, and they have degrees in, sanitary, service. And then stormwater is like something that gets added onto their job description when they come to a city where, so I think I'm also already seeing this trend. You're talking about, these services are going to continue to grow. We're going to have more and more assets. So when I think about, that, I love that idea of like, what's this going to look like in 20 or 50 years? I think we're going to have like stormwater maintenance professionals that are, there's like a professional certification for that thing, and you fully and deeply understand all the complicated things that go into the system. And then you start to think about, the slope of the apron or something like that, versus just this thing that you have to, maintain in your free time when you've already done all your hydrant flushing and you've already done all of your other, things that there's a lot of value built in the way that your organization is even organized around. So I think stormwater is just kind of like starting to rise to that level. our utility superintendent, like a couple weeks ago said, I predict that there's going to be like a professional certification for stormwater. And I was like, yeah, probably. And I'm going to, you know, be on board with that.
All right, let's take another question.
It's not a question, but it is on topic for what we've just been talking about. There is federal funding for stormwater projects, clean water state revolving fund, which is flawed in a multitude of different ways. But one of the most interesting ways in which it's flawed is this sizable pool of federal funding, which is growing, can only be used for new construction. And interestingly, EPA headquarters staff recognizes this flaw and has spoken in public venues recently and said that one of their missions right now is to find ways to expand the eligibility for federal funding to include maintenance. And that's a wonderful goal. And we all ought to do everything we can to help them get there.
Actually, if I take that to a question, what kind of successes have you had in being able to generate more funds to support maintenance? What kind of things have worked well to do that?
Well, we added line item in for our CIP because utilities had something sort of similar. So we're like, ooh, we just want to copy that sort of fund. But yeah, every year then we're just keep inching it up. But that's what's working for us.
Okay.
Money. I think a stormwater utility fund, I don't know how prevalent that is in Minnesota. I feel like a lot of communities have that, but maybe nationally that's less common, but just kind of that pool of funding that's dedicated to stormwater things. And then we've also kind of used that CIP angle. That is a little bit trickier for maintenance things where you're like, we want to be able to react and respond to this stuff versus we're going to build this, you know, sexy new thing. But it's been, we're still kind of ramping up. I think there's a lot more needs than we fully understand. So we haven't even really fully programmed them into our CIP yet. So it's been small enough that it's kind of like in the scheme of your stormwater utility, which is in the community that I'm in, you know, millions of dollars annually, then the stormwater maintenance piece is pretty small. But I think that's really underrepresenting the actual need. So there's some work there to just even understand like what's the condition and the need and all of these things. And maybe that's even the first step is just to get a picture of the liability.
Yeah. Other thoughts on generating funding? All right, well, we are quickly approaching the end of our time. So I'm actually going to move into our closing question. And the closing question here is, what would be your key takeaways? So it can be if you want to re-highlight something that was said that you really want to emphasize for audience to take with them today. If it's something new that we haven't been able to discuss, but you want to get it in, this is your opportunity to share your key takeaways from today's conversation for our audience. So I'm going to start on this side with Greg, and we'll work all the way down to Virginia. Greg, please go ahead.
That reminder on slopes for inlet areas for getting effective capture of sediments was a great reminder for me that I'm taking home, and the weir are the permeable barrier construction of that mixture of sizes there. So those were take homes for me.
That's great. Jessica.
Thinking about optimizing those from a design side and a maintenance side, right? Because as you mentioned, we're only going to grow in the assets that we have and the criticality of those as we're trying to meet these clean water objectives. So I think, you know, how do you optimize? Can you make these small little changes or adjustments or frequency or, you know, inspection style things to just make those systems simpler to maintain over and add value that way?
Ab, what would be your takeaways today?
Yeah, I was just going to restate once again the value and meaningfulness that I see in maintenance. I feel like it's often seen as like a burden or an obstacle, which are words that I've thought of as well. And it can be challenging to think, oh, we can't just install these systems and walk away from them. But it's also very meaningful as humans to interact with our landscape in that way. And I do find my job frustrating at times, but I also find it very interesting and engaging. And I really enjoy being part of, maintaining and caring for the stormwater systems that are super important to my community. So I think that maintenance is very valuable.
Virginia, give us the last word, please.
So I like something that you said earlier, which was simple steps frequently. And that's something that I want to sit and think about a little bit more. But that was, how could we think about that around our designs and really think about designs where you could have simple steps with a manageable frequency to make this really obtainable. But I also like this idea of engaging the community. And I know we didn't really go into that too much, but the potential of using this as a conduit to engage the community in their environment, and then all of the co-benefits that come out of that too, and everything else. And I think that's an area that warrants a lot more investigation, and just how to really do that in a thoughtful and sustainable way.
That's wonderful. Thank you very much. Thank you, panelists, for providing those key takeaways. We are now going to be at the end of our seminar series. I want to thank our panelists for being here today. I want to thank Virginia for giving us our keynote talk and setting the stage. I want to thank you, the audience, for being here in person or online and joining us today. I hope you enjoyed the seminar. I hope to also see you at a future Stormwater Seminar Series event. The links are in the chat for those of you online to check the schedule and see what's coming up. Our seminar in January will actually be talking about coarse sediment and what do we see in stormwater. So it'll be kind of an extension of today's talk today. So I hope to see you at a future event. Thank you for joining us today and have a great rest of your day.
Thank you.